Before I launch into chapter 2, let me do just a little work to situate it, to tell you where it is in the structure of the class. Well, in the last chapter, primarily what I did, yeah, I talked a little bit about what we do in the class. That's, proof. But mostly what I did was define core terms for the class. I showed you how to draw diagrams, how to name the objects within those diagrams. So it was really definition and diagram. That's what we were up to. And those are absolutely essential skills that you have to have. Of course, that's not really the point of the class. The point of the class is proof. But it had to be done. Now, here in chapter 2, we'll begin to talk more explicitly about postulates. But again, this is a proof class. So this is all the purpose of all of this is to get us to that point where we are able to give our first proofs. So I won't simply state postulates for you, and you should have some idea of what those are. You've seen them before. I won't simply state them. Instead, I will begin to discuss what you do with postulates. And what you do with postulates is you make inferences based upon them. So what we're really up to in this chapter is, well, yes, we state postulates, but we draw inferences from these postulates and also from the definitions of the previous chapter as well. And then we begin to get a sense of what really this work that we've done in the first two chapters, definitions and then postulates, what that does for us later on. And we begin to get a sense, I will explain this to you, of what proof really is. So here we go, geometrical postulates. Now, some of these you have seen already, but I'll pretend that you haven't. Um, some of the postulates that we've seen before will fill out. So, you will have seen a bit of it, but you'll see the rest of it this time. I have in mind in particular the ruler and the protractor postulates, but let's start on the assumption that you don't really get yet what a postulate is. So I'll build from the ground up. So we will need to make certain assumptions, okay? Some of our assumptions will concern the existence of certain kinds of objects, like when lines, for instance, exist, or when midpoints exist, or um, when angle bisectors exist, and so on. So we'll have to make assumptions about existence, and we'll also have to make assumptions about relationships between objects that we have seen in this class, and there'll be postulates of this variety all throughout the class, and I'll give you the first set here. And these are, as I said, assumptions, basic assumptions. Okay, so we'll make no attempt to prove that they are true. Now, we will talk about them to explain what they mean, but we will make no attempt to prove them. Now, this shouldn't bother you, and hopefully it will not bother you at any point throughout the year, because once you understand what these postulates, what they really say, I believe that you will find them obviously true. Obviously true. And all of these are found on my site, so simply look for the link on my site that says definitions, postulates, theorems, constructions. You'll find a PDF document that contains all of these. All right, so here's the first of them. And again, this is one of the ones that you've seen before. And I've attempted to illustrate what this really does for us. It's the line existence postulate. It says that if we're given 2 points, then we know that a line exists that passes through them, and we know, moreover, that that line is unique. That is, to put it slightly differently, given a pair of points, one and only one line passes through them. So look at the diagram. On the left-hand side, we start simply with a pair of points A and B, and then we have an arrow to indicate what follows from the existence of those 2 points, and what follows is the existence of that unique line that passes through them. That's our line existence postulate. Now, the ruler postulate, you've seen this before. You've seen part of this before. Now you're about to see all of it. What you saw before was clause 1 of the ruler postulate, which says that every segment has a unique positive length. Okay, we talked quite a bit about that in the previous chapter. What we said is that with every segment is associated a unique positive real number that gives the length of that particular segment. And so here we say it again. Now, clause 2. Clause 2, as it were, goes backwards, okay, from clause 1. In clause 1, we begin with a line segment, and we say that because we have this line segment, it must also have a unique positive length. In clause 2, we begin simply with a line that I'll call L and a point P on that line. And then what we do is this. Instead of begin with a segment cut out of a line and give it some length value, instead we start with a value that will represent a length. And then we say that 2 points exist, call them X and Y, on that line L, one on one side of P and the other on the other side of P, such that the lengths of the segments that are created when we drop in x and y, that is px and py, are both that real number that we chose r. Okay, I know that's a bit complex. I'll show you a picture in just a moment, but really once you understand the idea, I think you'll find it fairly simple. What it really says is this, is that if you've got a line and a point on the line, and you want to carve off segments of some particular length, well, you can do that. You can carve such segments out of your line. You can carve one segment from your line on one side of your point, and you can carve another segment of that same length on the other side of your point. So let us see a diagram to illustrate this idea. So let us say that we wish to carve out segments of length 3. That is, let our real number that represents length, let that equal 3. Okay, so what we start with is simply a line called L, then a point P on that line. Okay, so that's what you see on the left-hand side. And then what the clause 2 of the ruler postulate allows us to do is this. It allows us to add in these points x and y, one on one side of P, the other on the other side of P, such that the segments created, namely Px and Py, both have length 3. Okay, so again, clause 1 of the ruler postulate says if we're given a segment, it has a length, a unique positive real that represents its length. And clause 2 says this, that we can create segments. We can carve segments out of a line with any given length that we choose. Okay, one on one side of a given point, the other on the other side. All right, the segment addition postulate, which I believe you saw on one of the assignments that I had you do, and it's really quite extraordinarily plausible, and it's also, I think, quite easy to understand. So let us say that we have a segment AB, and let us say also that C lies on that segment between A and B, as is shown in the diagram. Then AC plus CB is equal to AB. Notice what AC and CB are. AC and CB are the two subsegments, call them, created when C is dropped into the interior of segment AB. And then what this really says is that part plus part, AC plus CB equals whole, that is AB. So you should find that quite extraordinarily plausible. And it should come as no surprise when I say that we'll have a postulate for angles that works in the same way. All right, so now let's begin to talk about angles. The protractor postulate, first of all. Clause 1 is very much like clause 1 of the ruler postulate. Clause 1 of the ruler postulate says that every segment has a unique positive measure. And clause 1 of the protractor postulate says that every angle has a measure between 0 and 360 degrees. Okay. And notice that I mean to say here that that angle measure will be greater than 0 and less than 360. And no doubt you find this extraordinarily plausible given what we have said we mean by angle measure. Now, clause 2. Clause 2 works in very much the same way as clause 2 for the ruler postulate does. And remember what clause 2 from the ruler postulate allows us to do. It allows us to create segments of a given desired length. What clause 2 of the protractor postulate allows us to do is it allows us to create angles of a given desired measure. Okay, so let us say that we start with some ray AB and some measure, some real number r between 0 and 360. That will be the measure of the angles that we create. Then here's what we can do. We can create two rays with that same endpoint A, call them AC and AD, such that the angles formed when we add in those rays, that is ABC and ABD, both have that measure of R. So let me show you a picture to illustrate clause 2. So let us say, just for sake of example, that the angle measure that we want is 30 degrees, so R is equal to 30 degrees. So what we begin with, you see this on the left-hand side, is the ray AB. And then what clause 2 of the protractor postulate allows us to do is to add in rays AC and AD, you see them there on the right, that create angle CAB on the one hand and angle DAB on the other, such that each of those angles has the desired measure. Okay, so again, what the protractor postulate says is this: every angle has a measure. And second, clause 2, if we have some ray and some measure that we wish to create, then we can we can create two rays coterminal with the original ray, such that we get two angles, one on one side, one on the other, really, that have the desired measure. Okay. All right, so there's clause 2 illustrated. All right, the angle addition postulate, no surprise that we have this. We had a segment addition postulate, so of course we have an angle addition postulate. With segments, we split a segment into subsegments. So what we'll do in this case for angles is we'll split an angle into some angles. So in particular, let's say that we have an angle ABC and some point P in the interior of that angle, then when we create that ray BP, the ray that splits the original angle ABC up into two subangles, then the whole ABC is the sum of the two parts ABP. There's ABP and PBC, the second part. So again, what it really says is just that the whole is the sum of the parts, in this case for angles. Now, straight angle postulate. This is something we have to be really careful about. Recall our definition of straight angle. Okay, our definition of straight angle is this. It is an angle whose two sides form a line. That's all that it says. Nothing in the definition mentions the measure of such an angle. Okay, but no doubt you have a belief about what the measure of a straight angle must be. Then here in the postulate we say what that is. It says, first of all, that all straight angles measure 180 degrees, and second, only straight angles measure 180 degrees. So let us make sure that we understand the difference between these two parts of the straight angle postulate. First, all straight angles measure 180 degrees. That means that if we're given a straight angle, if we know that a certain angle is straight, then we may say that it is 180 degrees. And the second part, the part that says only straight angles measure 180 degrees, that means that if we have an angle that initially we don't know it's straight, we're not told it's straight, but we do know that it measures 180 degrees, then we may say that that angle is straight. So another way to put this is that if an angle is straight, then it measures 180. That's the first part. And then the second part is if an angle measures 180 degrees, then it's straight. That is, it goes both ways. Now, let's begin to talk about what postulates do for us. They don't just simply sort of sit there as inert facts that we're just supposed to simply memorize or whatever we would do with them, but instead they are what I will call engines of inference. They allow us to move from one given statement to another statement. They allow us to infer a second statement that must also be true. The definitions also that we gave in chapter 1 will do this as well. And ultimately what this means is that they allow us to build proofs. Now, we're not really ready yet to begin to construct proofs, but that's ultimately where we're headed. And that's what we do in proofs, is we make a sequence or we make a set of inferences. So what postulates and definitions as well allow us to do is they allow us to construct proofs. Now, what do I mean really? That um, a postulate allows us to make an inference? Well, what we really need to do is to look at particular examples. What I mean is that the postulate tells us that some new statement will follow from a given statement. And I think the best way to explain what I mean by follow from is to look at examples. Okay, so here's what I've got, and this is what you'll find on the assignment as well. So I want to know whether we have a genuine inference. Okay, that is, in each of these examples, we'll have two statements separated by the word thus. And what I want to know is whether the second statement, that is the one after the thus, follows from the first. And if it does, I want to know what definition or postulate allows us to say that it does indeed follow. And that's what definitions or postulates do again. They tell us that in certain cases, a second statement follows from the first. Okay, so let's look at the example. That's enough sort of abstract theoretical talk about this. We need examples. So points F and G are given, okay? Tell you what, I'll draw a diagram. Points F and G are given. Thus, a unique line exists that passes through them. Okay, so what we want to know is if we are given that first statement, will the second statement, that is, a unique line exist that passes through them, will it follow? Will it also be true? And the answer is yes. Okay, that second statement after the thus does follow from the first before the thus. And by what does it follow? Well, go ahead and draw it in. It follows, of course, by the line existence postulate. Okay. So what does the line existence postulate do for us here? It allows us to take a given statement and write a new statement. Okay. That then has moved us forward, right? So initially all we had were 2 points, and then we also have a line. Okay. So the line existence postulate has actually introduced something new into our diagram, and that's extraordinarily important. So how about this one? Again, we have two statements separated by the word thus, and we want to know whether the second really does follow from the first, that is, whether we have a genuine inference. So let's see, what do we have? Angle 1 is right, thus angle 1 measures 90 degrees. Yeah, angle 1 measures 90 degrees. That really follows from angle 1 is right. Okay. Now, by what does it follow? What definition or postulate tells us that if an angle is right, it measures 90 degrees? Well, of course, that's simply the definition of right angle. That tells us that right angles measure 90 degrees. Okay, so how about this one? Angles 1 and 2 form a linear pair, thus angles 1 and 2 are both right. Well, perhaps a picture to illustrate this. So let's create a linear pair. To create a linear pair, you draw a line, and then you choose a point on the line, and from that point you construct a ray. So the angles 1 and 2 that I've just created, those are definitely a linear pair just by definition of linear pair. Now, does it follow that they're both right angles? No, it doesn't follow. That doesn't have to be true. It could be true, but it doesn't have to be true. For instance, angles 1 and 2 could be, I don't know, 120 and 60 degrees, right? And then, of course, it would still be a linear pair. That is, it would still be straight. Yeah, so that second statement, the one after the thus, simply does not follow. There is no reason to assume that angles 1 and 2 must be right. Okay, so yeah, linear pairs don't have to be right angles. That doesn't follow. Okay, here's another one. B is the midpoint of segment AC. Okay, so let's draw the picture to illustrate, and let me recommend to you that in any case where a picture has not been drawn to illustrate a particular statement or set of statements, draw the picture. Pictures, as I said back in the previous chapter, are really what makes this appropriate, geometry appropriate for a first proof class. Those pictures are invaluable aids to the imagination. Okay, so we have B as the midpoint of segment AC. Okay, so I add the hashes to indicate that indeed B is the midpoint. Does it follow that AB is equal to CB? Yep, it does. Okay, that does absolutely follow. And by what does it follow? It follows by the definition of midpoint. Okay, so one more, a fifth. AB is equal to CB, thus C is the midpoint of segment AC. Let me give you a second to ponder that one. Perhaps draw yourself a picture and ask yourself whether the statement after the thus follows from the statement before the thus. Now, many of you will have said that it does indeed follow, but it does not. Okay, here's what many of you assumed, no doubt, that all of points A, B, and C lie on a line. Now, there's nothing in the given information, which is that AB is equal to CB, that requires that all of those points A, B, and C lie on a single line. So for instance, here's a diagram that is perfectly consistent with the given information. Okay, so let's say that we have A and B and C arranged as you see, so that A and B and C are not all in a line. That's perfectly consistent with the given information. That is a very real possibility. And then let us ask ourselves whether, oops, I meant to say B here. So sorry about that mistake. So let us ask ourselves whether B is the midpoint of segment AC. And the answer is no, because what does midpoint mean? Midpoint means, I think it's good here to switch to a different color. Midpoint means that we create the segment from one point to another, and then on that segment, we place that point, call it perhaps M, such that the two subsegments created are equal to one another. That point M is the real midpoint of segment AC because it does actually lie on the segment AC. The point B is not the midpoint of segment AC. So to the question, does it follow that B is the midpoint of segment AC? Absolutely, it does not follow that B is the midpoint of segment AC. Now, if we were to add to the given, which was AB is equal to CB, if we were to add that all of AC and B indeed are collinear, then it would follow that B is the midpoint of segment AC, but we were not given that information. And since we were not given that information, it simply does not follow. So there it is. It absolutely does not follow. All right, so that's it. Next time, we'll begin to talk about algebraic postulates, of which we have a number. And then we'll begin to construct what I call inference chains, where we don't simply have one statement that follows from a second statement, but rather we'll have a second statement that follows from a first, and then a third that follows from the second, and so on. And that will begin to look very much like proof.